Okay, so just before we ascend the next step in our staircase of future engineering, where we're going to be looking at the evolution of industry, let's stick with academia for just a little longer as we hear a presentation from our keynote headliner, Professor Mark Miodownik. Now, Professor Miodownik's CV is quite incredible. In his day job, he is the director of the Institute of Making and an internationally renowned materials scientist at UCL. He currently focuses his research efforts on self-healing and self-organizing materials. But perhaps Mark is more widely known for his work in broadcasting, having presented dozens of TV and radio documentaries, including things like hugely popular TED-Ed lessons, as well as the Royal Institution Christmas lectures, and my personal favorite, Mark, is the scientist in residence on Dara Ó Briain's Science Club. Anyone who thinks that comedy and science make odd bedfellows really needs to check out that show. But Mark is also a critically acclaimed pop science author, and his book, Stuff Matters, not only received rave reviews amongst the British press, but it quickly became a New York Times bestseller. And it is this unrelenting dedication to science, communication and outreach that led Mark to receiving the Royal Academy of Engineering's Rook Medal for public engagement. Incredible. So ladies and gents, as I sidle off to the edge of the stage to enjoy this presentation along with you guys, please give a very warm NIDays welcome to Professor Mark Miodownik.
Thank you very much. That was a bit too much, bigging up, but sometimes it's nice. If only, if only my dad was here to hear it. Okay, I just wanted to talk about what I get up to in the lab, why I got involved with starting something called the Institute of Making, and also I'm going to give you a small idea of the kind of things that are boiling up out of the Institute of Making at UCL, and a student project which sort of fits in very well with the theme so far. First of all, I just wanted to go over to my slides and see, this is just a picture, an ordinary picture of a London scene, it's not very far from here on the Strand. And the why I'm a material scientist, why I care about this stuff is that looks a bit boring, maybe, but as soon as, if you're a material scientist, this is what you think as you're walking down the road. Oh yeah, paint. Great material that. Glass. What would the world be like without ceramics? Anyway, it's not always like that, but the point is that actually you don't have to spend very long, and you realize that that scene of mundanity, apparently, is teeming full of materials, and if they weren't there, we would all be standing in a muddy field now. Actually, it's quite a good, nice day outside, so it wouldn't be so bad today. But tomorrow, or yesterday, if you remember how bad it was raining, just think. Shelter, materials, the ages of civilization are named after materials. You have the Stone Age, and then you have the Bronze Age, you have the Iron Age, and so forth. Each one of these materials is a revolution in its time. And of course, if you took them away, we would be much the poorer for it. We probably wouldn't be human, really, in that sense. But I don't want to kind of go on. I haven't got much time, so I don't want to go on about how great all these materials are. I want to talk about the future, where material science is going, where materials engineering is going. And I'm going to draw your attention to a little circle around life in the top right-hand corner. Because living materials, living matter, however good we think our stuff is much more impressive. And trying to take a slice, trying to get some ideas from living matter and incorporate them to modern materials technologies is where we're going next. And is also part of the reason why we had to start something called the Institute of Making. So just to give you a sense of why I think that's really true, I've drawn a map of the world, but this is a map of scale. This is big things at the top and small things at the bottom. And on the right and on the left here, as you look at it, I've got the living world, and on the right, I've got the man-made world. And so what you have things like trees and whales, and then you get mice, and then you get the fleas on the mice, and then you get the hairs on the fleas. And if you zoom into those, you get these multicellular things. And then they're tissues, and all of us, our skin, our brains, almost all of our makeup is this multicellular tissue-like material. And then individual cells. So this is the Lego block of the biology world. And these are incredible things. You and I, we all started as a single cell. The tree, the whale, all started as a single cell. I mean, biology builds things by starting with one cell, dividing. But it makes ceramics, it makes plastics, it makes fluids, it makes things that self-heal, it makes things that can reproduce themselves. It does it all with that building block. And that's really very impressive indeed. So you and I, if you get hurt in your hand or you get cut, it will heal itself. You can feel the cut. So we're embedded with sensors, we've got actuated systems. It's all part of who we are. It's all part of this multi-scale matter. Now, on the man-made world, as I was saying before, obviously materials are the big deal, but we can make big things like buildings out of them and robots and phones, and if you zoom into those, you have tiny little wires, and you zoom into those and you can see little MEMS devices which have features smaller than the hair of a flea, so that's pretty impressive. You're thinking, what's he going on about? We've done a really good job so far, and you have. But even if you zoom further into that, and you've got crystals, and we understand how to manipulate those and make jet engines, and if you zoom in further, you have an individual single transistor down there, and the billions of those are connected up in your phone, in your laptop, in all of this NI technology you see around you. So that's impressive, right? And if you zoom even further in, you get these things at the bottom. That's a carbon nanotube, and nanoscale materials self-assemble. So you just put the right conditions in place, and then they just pop into being. So all of that looks very impressive, and it is, except for almost none of it really connects up. So unlike in the biology world, where you have embedded sensors and in your hands and your arms and your head, and you have computation and information flowing up and down the scale. So everything right down from the DNA inside each one of your cells, all the way up to the biggest part of you, your brain, your living consciousness, there's a communication going all the way through your being, right? And in some ways, you might argue that is what life is. But could we imitate that in the non-living world? Could we make artificial living matter? Could we make a bridge that can heal itself? Could we make a bridge that knows its damage? Could we make a motor? Could we make a house, a building? Anything, in fact, that has that integration across the scales. And when we start thinking about that's the real challenge of the 21st century for materials, when we start thinking about that, we realize that the problem is that each one of those scales requires 20, 30 years of hard work just to get to the edge of where knowledge is at the moment. Each one of you in this room probably knows this. So if you want to get anything done that links those scales up, you have to have experts in each individual realm. You have to have quantum mechanics people, you have to have nanotechnologists, you have to have microelectronics experts, you have to have chemists, you have to have, and as you go up the scales, you realize that the people that you're starting to call out are not technical people as we would think of them, but they're things like anthropologists, how things behave. They're things like archaeologists. They're people who understand, they're designers, they're architects, right? You've got to have architects involved if you want to make a building that self-heals, and you want to have a building that has integrated sensors, a building that moves, that can control its temperature dynamically in the weather. You need those people to be talking to nanotechnologists. And the whole design of the whole building has to be as integrated as in biology. Now that's tricky because those people these days don't get to meet. How many architects in the room today? Right? I mean, we silo ourselves because we're always trying to get to the edge of our own profession. And so we need a place where we can all meet, where we can really go for the big integrated technology problems. And I want to highlight carbon as a real tangible example, because you know that airplanes are now 60-70% carbon fiber. So that seems like it's working, right? And cars are getting that way with the Tesla, and bikes are starting to become carbon fiber. And as you go down the scales, you hit the point where the engineers who design stuff like airplanes and cars and make that stuff, they no longer talk to people who make graphene at the bottom, which is the strongest, most extraordinary material that's sort of come on the scene recently, 2010 Nobel Prize. They no longer talk to those people because no one can make graphene into carbon fiber yet, not even remotely. And so no one wants to talk to them because it's like the next horizon for Boeing or Airbus is 5 years away, so why would we talk to graphene people? So it seems like a really big leap to be able to think of even that a plane of the future might be made of a carbon fiber that is a graphene based. But that to me is the challenge. And not just that actually we should be using graphene's electrical conductivity to embed sensors throughout the whole plane so we know exactly what's happening, the stresses and the wear, and that should all feed back in local communication and into a kind of internal nerve system, and perhaps even a self-healing actuation. Sounds like science fiction. But I really think we can get there, and I think that the way we're going to get there is by finding a place where people at every single scale that needs to be solved can actually work together. And so our go at this is the Institute of Making. And it's a lab for everybody in UCL. Whether you're an English student, you're an anthropologist, whether you're a chemist, a physicist, engineer, you can be a member. It's free. And we will bring you up to speed on any technology you want to learn. So we do master classes, we do, but mostly actually it's the people themselves who teach each other. That's the aim. We on purposely kind of try not to make a hierarchy of different materials. So all materials for us are interesting. We have a big collection of materials library. We try to get people hands-on immediately to make stuff, and not just high-tech stuff, or rather, I'd say that blacksmithing, and as an example of it, is high-tech, actually. You can feel in your hands the dislocations moving in the crystals. So to get people really engaged in new materials and old materials technologies, get them making stuff, playing around, talking to artists, talking to architects, talking to designers, talking to the people who understand the human interface of materials. We've got a space where you can not only talk a bit of theory, but you can also make. We've got workshops in the same space, and we really just encourage all of our members just to get stuck in, whatever discipline they are, because our aim is to ignite collaborations and mutual appreciation between disciplines for making prototypes. And I want to just talk about one prototype that came out of our lab, because I think this sort of illustrates what's important about it. So James Cook, who's a student of mine, third-year engineering student, came to do a project with me. I'm a cyclist, he's a cyclist. We're like, well, bike helmets, what really annoyed us is if you look at the stats on bike helmets, even though the green line there is going up in terms of the amount of wearing of bike helmets, there isn't a big step change in the injuries you get whether you're wearing one or not. So injuries are going down, but they're not going down because people are wearing helmets, essentially. So why is that? We were wondering, why is that? And could you design a better helmet? And in the end, came to the conclusion that when you talk to medics, and that's why having something like the Institute of Making is important, because you talk to fashion designers, and they say, well, people don't like to wear helmets. You talk to medics in the space, and they say, oh, it's because the British standards is all about normal impact, and most injuries are not on normal impact. Most injuries are rotation of the brain. So actually, as you're falling off your bike, or you've been plunged off your bike, and you hit something, bang, like that, you've got rotational force, and that is what rips the cordons in your brain. And so a lot of the injuries, a lot of the brain damage, is not because something went into your skull. It's because internally, the rotational degree of freedom of your brain was not absorbed. That energy was not absorbed. So what you need is not just a normal compression material. You want a material that can absorb rotational energy too. And if possible, you'd like a helmet that knows you're in a crash, right? Has already got instrumentation in it, knows you're in it, and will deploy the right type of energy absorption. That sounds mad, but actually possible, because these days, as you know, with 3D printing and integrated electronics, you can actually, make materials that can absorb energy to any level you like, because complexity sort of comes for free with 3D printing. So you can make things that are designed to shear in one direction or designed to shear in another direction. And you can also make interlocking joints that lock up under certain conditions, or let the shear happen under other conditions. And also, this can all be done to order, right? So all of you can have your brains scanned, and this helmet can be printed to fit you. So you have a 3D printed helmet that has integrated mechanics designed to help you in a crash, but also exactly fits you. So again, helps you with the safety. And this is what the bike helmet ended up looking like, the first prototype. And the important thing for me, and I've never been in this position before, is that we could support every level of this. And in fact, NI Instruments were really brilliant, because what we really needed to do was test this concept and make sure we could meet the British standards early on in the project. And you can see some 3D printed samples here of different types of energy absorption. And our test rig and the NI instrumentation was just great. I mean, that's what you want. You want someone who can run with the ball, who can have an idea and fully prototype it within 9 months of the project, having had no background in instrumentation, no background in 3D printing, no background in designing a fully product, no background in brain injury. But he picked all of it up because we could facilitate that, and we had a partner in NI instrumentation. So thanks very much, guys. And this is the result, which is the first stage prototype. So a fully fitted prototype. Actually, UCL backed him. They gave him money. He started a company. So the first time in my life I've ever had a third-year project turn into a company before the project was submitted for. And I'm just really proud. I mean, I think that just shows, and this is, I think, just a taste of what is possible if you give people the right, if you basically make prototyping the focus of engineering, and you give people a massive range of people to collaborate with across the whole ranges of scale of discipline. And so this is up for grabs now, I think. And I've been to lots of companies recently which are setting up places like the Institute of Making internally in their companies because they want to stop the siloing. They want their own people to have one day a week where they can do something a bit crazy with some other people in the company that isn't a product that needs to be on the table in 10 years' time or even 5 years' time, but actually is about future looking, is about trying to really push the technology. And I really believe that this works. We've seen it works. And yeah, that's really all I wanted to say, which is that the real future of a lot of the technology you're going to see in the next 5, 10 years is about integrating different scales of technology, 3D printing, sensors, actuation, all becoming part of one made object. So buildings that can heal themselves, sense themselves, planes that can do that, clothes that can do that, clothes that can distribute medicine, clothes that can monitor your health, wearable tech, it's all going in that direction. But what it really needs is an integration, not just of the technology, but of the people. And so its place is important as technology. And with that, I will thank the people, because it's actually this set of people who make it happen. I'm just one person in a cog of this big organization, and very proud to be part of it. Thanks for listening.